Hi. In last class, we discussed about series resonance. Now we are discussing about parallel resonance. In parallel AC circuit, the resonance in parallel AC circuit will come at susceptance will make 0 and the current and voltage will be in phase and the power factor is at unity. Then it is said to be the parallel resonance circuit. For parallel resonance in RLC circuit, we are taking as R, L and C connected in parallel with the voltage, and the current supply voltage will be I, and the admittance with respect to the resistance is 1 by R, with respect to the inductance will be 1 by JXL, with respect to the capacitance will be 1 by JXC. 1 by R will be the conductance, 1 by XL and 1 by XC will be susceptance BL and BC. Then overall admittance we will take as Y is equals to G plus J, BC minus BL. At resonance, the susceptance is going to be 0. That BC minus BL is equals to 0. By making it, we find the resonance frequency as FR is equals to 1 by 2 pi root LC. The frequency versus admittance graph will be like this. This represents the inductance and this represents the capacitance. For capacitance is always leading and for inductance is always lagging, and the inductance, the susceptance BL will be inversely proportional to frequency in that if frequency is going to be increases, that BL is going to be decreases. In BC, susceptance with respect to the capacitance, frequency increases, it going to be increase in this, and the resistance is neutral and it is called the conductance, and that intersection point of these two we will call as the resonating frequency FR, and this part is for inductive circuit and this part is act as capacitive circuit. At capacitance BC greater than BL, at inductance BL greater than BC, and at this point for inductive BL minus BC, for capacitive BC minus BL. At this conductance point BL is equals to BC at resonance. Conditions at resonance in parallel circuit. The inductance and capacitance are equal. Net susceptance is 0. That net susceptance will be BC minus BL is equals to 0. What? BC minus BL is equals to 0, and admittance is minimum and equal to conductance. That we all know that impedance is equals to resistance, right? That is applicable over here. That impedance is equals to resistance is at series resonance, and at parallel resonance admittance Y is equals to conductance Z, and the current is minimum. I is equals to Vz, and V and I are in phase and power factor is unity. These are the conditions for parallel resonance circuit. The current in parallel resonance circuit is determined by, this is the supply current, this is the IR and IL and IC. IR, IL, IC are the branch currents, where between the IL and IC the circulating currents will found, and the overall current in this branch, in this total circuit is I is equals to IR plus R minus J, IC minus IL. from this, I absolute value of current will be IR square plus IC minus IL whole square, and where IR is the voltage drop across the resistance is V by R. The voltage drop across the resistance is V is equals to IR, and the current will be IR is equals to V by R, and IL is equals to V by XL, and IC is equals to V by XC. And at resonance, the current IL and IC are equal. At resonance, IL and IC are equal, and these are 180 degrees out of phase. When IL is equals to IC, and at that time they are 180 degrees out of phase, then the resistance current is minimum, that is I minimum. And where IL is equals to IC, by equating this we get the resonant frequency as F is equals to 1 by 2 pi root LC, and the current in resonance circuit will defined as, and this is the resistance. For the resistance it is going to be neutral, it doesn't change, and for this inductance, for the inductance it is lagging. For that lagging, it's starting from 0, from F varies from 0 to infinity. At 0 it is at high point, and at infinity point it reaches the resonating frequency. That, and at the capacitance the voltage and current, for the capacitance current is leading. For that leading circuit, if the frequency is increases, the capacitive current is also increases. For the inductance it going to be decrease, and the 2 points, the points where the inductance, capacitance and resistance meet is known as the point F0. That F0 is nothing but the resonant frequency. At resonant frequency condition, IL is equals to IC. And at this condition, at the minimum value of current, the resistance will obtain. That resistance is nothing but the Z. So, the minimum value of current I minimum is equals to IR. Okay. The frequency response curve with respect to the current is shown over here. That all explained, and current is out of 180 degrees out of phase, and IL and IC are equal. By that resonating frequency we determined. Then Q factor. What is the Q factor in parallel resonance circuit? Q factor is defined by the ratio of circulating currents to the supply current. What is circulating currents with respect to the capacitor is IC by I. With respect to the inductor is IL by I. What is IC? V by XC. And V by XC, by solving this R by XC we get XC is 1 by omega C. By this omega CR we will get, what is omega? 2 pi F0 CR, where F0 is the resonant frequency. We all know that resonant frequency will be F is equals to 1 by 2 pi root LC. Just we are substituting F0 in F0 place, we are substituting 1 by 2 pi root LC. With that we get the quality factor Q is equals to R root C by L. For in case of inductance also we substitute the resonant frequency. By that the quality factor with respect to the inductance and the capacitance are going to be equal in a parallel resonance circuit. That quality factor in resonance circuit is nothing but the R root C by L is the quality factor for parallel resonance circuit. And where the quality factor will gives the current magnification in parallel resonance circuit, and In a series resonance circuit, it is said to be the voltage magnification. Quality factor in parallel resonance circuit which we got is the inverse of the series resonant circuit. Bandwidth is measured for parallel resonance circuit between two half power points. These are the two half power points, and the resistance. For the resistance, we get the steep curve for series resonant circuit because voltage is directly proportional to impedance. Voltage is directly proportional to impedance. For that sake, we are using this bandwidth of series resonance circuit for as well as parallel resonance circuit. By this, bandwidth is F2 minus F1, and half power points, that half power points is 0.707 0.707 Z max. We define the half power points, that F1 is the lower cutoff frequency and the F2 is the higher cutoff frequency, which I explained in a series resonance circuit. With this, we completed the bandwidth and quality factor and current in a parallel resonance circuit. And another thing, two branch resonant parallel circuit we are going to discuss now. A two branch resonant parallel circuit. In this two branch resonant parallel circuit, we are taking the resistances RL. For the inductance, we are taking the separate resistance, and we are taking separate resistance for capacitance RL and inductance RC and capacitance. And the admittance branch, this is one admittance branch and this is one admittance branch, and overall current we get here is I is equals to IL plus IC, and YL, the admittance with respect to this branch. By this, what we get? 1 by RL plus JXL. By rationalizing this one, we get the admittance across this branch, and the admittance across this branch will be 1 by ZC, 1 by R minus JXC. By rationalizing this, we get the admittance at the capacitance, and overall admittance Y is equals to YL plus YC. Just we are substituting this one, and we get the real terms as well as the imaginary terms. We all know that at resonance condition, we make the susceptance will be 0. That susceptance is nothing but the inductance and the capacitance. If we are making equal, that XC by RC square plus XC square minus XL by RL square plus XL square, we are making equal, that is equals to 0. By that, we are defining the resonating frequency. At resonating frequency, these two are equal, right? Susceptance is 0. We are making that susceptance is equals to 0. By that, we are defining the resonant frequency. And by making equal, what is XC? XC is nothing but 1 by omega RC, and XL is omega RL. Omega R with respect to the resonating frequency we are writing here. And by the solving of this one, just this observe this solving. By this, we get the resonating frequency F0 is equals to 1 by 2 pi root LC under root RL square minus L by C by RC square minus L by C. For an ideal capacitor, it two branch resonant parallel circuit will act as a tank circuit. What is that? At RC is equals to 0, that acts as the ideal capacitor circuit. It works as a tank circuit. In that, we are substituting the RC is equals to 0, while substituting RC is equals to 0, we get one by 2 pi root LC RL square minus L by C minus L by C we get. By this we get L by C minus RL square by L by C. With this L by C cancel, 1 minus C RL square by L we going to get. F naught is equals to 1 by 2 pi root LC under root 1 minus C root C RL square by L we get as the resonating frequency for the tank circuit. And parallel resonance circuit is also called as the rejecting circuit. In this, some frequencies are going to be rejected in this, and the current is minimum. When the current is minimum in a parallel resonant circuit, when the current is minimum in parallel resonating circuit, it rejects the all frequencies and it acts as a band pass filter. It rejects some frequencies and it acts as band pass filter, and it pass only some frequencies in the circuit. So we call parallel resonating circuit is called as rejector circuit, and series resonance circuit we called as acceptor circuit. And resonance at all frequencies is defined by making RL square RC square equal to L by C. We are determining the resonant frequency as undefined. At resonant frequency undefined condition, F naught is infinity and RL is equals to RC is equals to root L by C. It's said to be the resonance at all frequencies. This is about the parallel resonance circuit, and in this parallel resonance circuit we discussed about the parallel resonance circuit we discussed about the parallel resonance circuit and bandwidth, quality factor, and the RLC parallel circuit with respect to the inductor and capacitor. These are the things, and we also defined the frequency, resonant frequency at all frequencies.